Graphite powder forms the base material for battery anode production. The material is transported forward through a controlled screw conveyor system. The material is prepared for moisture removal before further processing. Screening ensures consistent particle size across the material. Measured quantities are prepared for the mixing process. The graphite is delivered to the next stage for slurry preparation. Graphite powder is introduced into the mixing system to begin slurry preparation. Mechanical agitation combines graphite with liquid to form a uniform slurry. The mixture develops into a uniform slurry with controlled viscosity. Filtration removes unwanted agglomerates to ensure smooth coating quality. Flow control ensures stable delivery for the coating process. The prepared slurry is delivered for electrode coating. A continuous copper foil forms the base layer for anode coating. Graphite slurry is applied evenly to create the anode layer. Drying removes solvent and stabilizes the coated layer. Compression improves density and bonding of the anode layer. The coated foil is collected for further processing. The anode material is prepared for the next stage of processing. The coated anode material enters a thermal conditioning stage for final stabilization. Preheating prepares the material for controlled compression. Automated inspection ensures uniform coating quality. The refined anode material is collected for further processing.
The anode layer is now fully prepared for assembly.
Lithium metal oxide powder is introduced as the active material for the cathode. The cathode material enters the mixing system for slurry preparation. Binder is added to stabilize the cathode mixture.
The slurry is transferred for refinement and filtration.
Continuous motion prevents material separation before coating. The cathode slurry is delivered for electrode coating. Aluminum foil serves as the base layer for the cathode coating process. Cathode slurry is applied uniformly to form the active electrode layer.
Drying removes solvent and solidifies the cathode coating. Compression improves density and performance of the cathode layer. The coated cathode material is collected for further processing. The cathode layer is prepared for the next stage of battery assembly.
The coated cathode material enters a stabilization stage to improve structural integrity. Preheating ensures consistent conditions before final compression.
Compression enhances the density and performance of the cathode layer. Inspection systems verify coating quality and uniformity. The cathode layer is now ready for electrode assembly. The refined cathode material is collected for assembly preparation. Alignment systems ensure precise positioning before the cutting process begins. The electrode material is separated into controlled widths for further processing. Each sheet is cut with consistent dimensions for battery assembly.
Automated stacking prepares electrode sheets for cell assembly.
The prepared electrodes move forward for battery cell assembly.
Electrode sheets are prepared for stacking into battery cells.
A separator layer is introduced to prevent electrical short circuits between electrodes. Layering continues to build the internal structure of the battery cell.
Light compression ensures stable contact between layers.
Inspection ensures precise alignment of all layers before final assembly. The layered structure moves forward for cell enclosure and final assembly.
The electrode stack is prepared for insertion into a protective casing.
The electrode assembly is inserted into the casing with precise alignment. Electrolyte is added to enable ion movement within the battery. Initial sealing secures the internal components within the casing.
The sealed cell moves forward for electrical activation and testing.
Leak testing ensures the integrity of the sealed battery cell. The battery cell is placed into a formation system for its first electrical activation. A controlled current begins the initial charging process inside the cell. A rest phase allows the internal chemistry to stabilize after charging. The activated cell moves forward for performance evaluation and quality testing. The battery cell is now electrically activated and ready for final testing.
Each battery cell undergoes detailed testing to verify performance and safety.
Internal resistance is measured to evaluate efficiency and performance. Voltage stability testing ensures long-term reliability of the cell. Mechanical testing verifies the strength of the battery casing. Tested cells move forward for final packaging and distribution.
Finished battery cells enter the final packaging stage.
Protective packaging secures the cells during transport. Packaged batteries are transported to distribution points. Battery cells are assembled into packs for real-world applications.
The final battery powers real-world technology used every day.